Emotional Disabilities at the University of Potsdam in Germany. I have other appointments as an adjunct professor at Purdue University and most recently as a research associate with the Center for Augmentative and Alternative Communication over at your place at the University of Pretoria. Thank you so much for inviting me to talk to you this afternoon. We will have 2 days together, one day on visual analysis and the second day on statistical analysis of single case experimental designs. We're going to start out with a little bit of review of the major tactics and major designs, and then I will go straight into visual analysis for today. And like I said, for tomorrow, we're going to cover more of the statistics, more of the statistical options that you have when analyzing data from single case experimental designs. All right. Let's start with a brief review, and please feel free to interrupt me anytime through the chat function, and I'll see if I can answer your questions. So this session is about single case experiments, or another term for this is single case experimental designs, SCEDs for short. And these designs have become more and more prominent in communication disorders as well as special education, because they are very essential for demonstrating evidence-based practices. And they do that by examining pre versus post-treatment performance within a very small sample, oftentimes only a few students, could be anything from just one student, oftentimes it's 3, sometimes it's 4, 6, or even more. The approach is an experimental way of revealing a causal relationship between a treatment, an independent variable, and an outcome, a dependent variable. The designs employ repeated and reliable measurement. There are within and between subject comparisons to control for major threats to internal validity. You have to replicate this intervention effect, and this can be done in several ways, which we will see in a little bit. And you also want to replicate the experiment as a whole to enhance external validity. Like I said before, the single case experimental designs have now a very prominent role in establishing evidence-based practice, because they essentially help us determine which treatments do work and which treatments do not work. The individual participant is always at the focus, at the center of a single case experimental design. Sometimes, like I said, you can just run a single case experiment with just one participant, but typically these designs include multiple participants, 3 to 8 in a single study. Each participant serves as his or her own control, and then performance is being measured prior to intervention, and that is compared to performance during and or after intervention. In most cases, the research participant is an actual individual, but it is possible to build the case around a group of participants, and then that group performance is being taken and being measured over time. And you have for each measurement period, you have a single score, and that can also be graphed as a single case experiment. So the case can be an individual, or it can be several individuals that are measured as one unit, and then that little group is the so-called case. And these designs are nice. They are so important because they can demonstrate experimental control. And experimental control is typically documented 3 times, either at 3 different points in time within a single participant. We would call that within subject replication, or across different participants, and that is called intersubject replication. And then there's different ways of how we can document that this experimental control is achieved. For example, we can implement the treatment and we can withdraw it. We would call that the introduction and withdrawal of the independent variable. We can also introduce the treatment or the independent variable at different points in time to different participants. Then we have a staggered introduction at different points in time. We can also put the independent variable on and off across observation periods, or we can have 2 different independent variables. Sometimes the participant is exposed to type A, and sometimes the participant is exposed to the alternative option type B. That is called iterative manipulation of the independent variable, and we can also do that multiple times and then have a design that tracks that performance. So the major types of designs, there are three major types, a few more variations, but the three most commonly known design variations are withdrawal, multiple baseline, alternating treatments. And I'll walk you through each of these. In an ABAB design, we are going to be starting with the baseline, and then after a stable baseline is being created, we're going to be moving into intervention. As soon as intervention comes on, we should see an uptick in an increase in the frequency of the target behavior. And then the logic of the ABAB design is, as soon as we are going back to baseline, then we would be seeing the original performance again. And that is called a reversal, or a withdrawing of the treatment. You're withdrawing treatment here, and then everything reverses back to the original performance the participant had shown in the original baseline. Because you want to end on a positive note, on a phase that is actually beneficial to the participant, you're going to put on another intervention. This is then the second phase B, and again there's a reversal, and you should see what you've seen in the first B phase, that the same type of pattern emerges, that there's always higher performance in the B phases and performance goes down in the A phases. That is the reversal logic, or the design is called ABAB design. There are various variations. You don't always have to start with A. You could start with an intervention, then do the withdrawal, go down to A, and then come back to B. You could also infuse other treatments or variations of the treatment. Then this is called phase C. And in between, you can go back to A to demonstrate experimental control, then have another variation between those treatments in there. So the ABAB logic has a lot of flexibility in terms of how you want to start out, and in terms of whether or not you want to also infuse other treatment phases in that sequence. Usually you would want to end with a treatment phase rather than this baseline. You want to leave on a high note, so to say. You don't want to leave the participant without treatment. That would be kind of tricky for ethical reasons. Right. So question to the group: if you have an ABAB design, and here we're starting out with a high target behavior. This could be the out of seat behavior of a student. It could be the number of curse words or the inappropriate behavior a student displays. It could be something such as aggressive behavior of a student, self-injurious behavior that needs to be intervened with immediately. Then you're doing a treatment, and you can see that this high frequency behavior, it goes down to relatively low levels. And now you want to apply this ABAB strategy, and you're trying to go back to initial baseline levels, but it doesn't really seem to work. You cannot reverse that initial effect. The second A phase stays relatively low, and then when you're putting on treatment, the B phase also stays low again. What has happened? Right, think about it for just a second, and then because I can't hear you, I'll present you with the answer. Essentially, what has happened here is the target behavior is irreversible. Once you have changed it once, you cannot change it back. And that happens quite a lot in educational settings, or it happens with behaviors where once the student has learned what to do, the student cannot unlearn what you have just taught. The behavior modification cannot be reversed. So for example, if this is problem behavior and you have reduced the problem behavior, and the student has understood, okay, I am no longer supposed to be aggressive, I am no longer supposed to say curse words, out of seat behavior is not desirable. The student has fully understood that, and then even if you pull the intervention away, the newly learned skill is still sticking with the participant. So that's what's happening here. And then this design logic, the reversal, the withdrawing of the treatment, this does no longer work. You can no longer demonstrate experimental control under these types of situations. And then it is very important to switch over or to plan for another design tactic. And what is most often done is in these cases is switching to a so-called multiple baseline design. In the multiple baseline design, we do not have to withdraw the treatment can stay on, but we have other ways of replicating that intervention effect. And that intervention effect can be replicated across behaviors. This would be one participant, and the intervention effect is being demonstrated for behavior 1, behavior 2, behavior 3. It could also be that we are having 3 different subjects, subject 1, subject 2, subject 3, and within each participant, we are demonstrating this intervention effect. That's another strategy. Then the third strategy is taking one individual and having 3 different settings, and you're showing that the intervention can be replicated in setting 1, in setting 2, and in setting 3. So always we are starting with a baseline, but the baseline has different lengths. The second and the third baseline are being prolonged while the intervention effect occurs. This portion here provides experimental control for the intervention effect that is occurring up here. And this part here is the experimental control for the initiation of the effects in number 1 and number 2. So by having this staggered introduction of the treatment of the independent variable, I can create 3 different demonstrations of an intervention effect. So then there are questions, research questions that are of comparative nature, and we would call that comparative efficacy research. In comparative efficacy research, not only do you want to know if one treatment is effective, you want to compare it to an alternative. You want to compare the efficacy, sometimes even the efficiency of 2 different treatments or 3 different treatments. And the way of doing this is through an alternating treatment design. In an alternating treatment design, you can start out with a baseline. It is not always mandatory, but it is good practice to start out with a baseline in an alternating treatment design. Then you have 2 different, or in this case, even 3 different versions of the treatment. Number C is the same as baseline. You would be continuing data collection when the 2 treatments are not present. And then you have version A and version B of the treatment, which are being graphed at the same time, and you alternate them. You do 1 session on B, 1 session on A, and then again A and B, sometimes 2 times B maybe. You should randomize that sequence, and then you can contrast those 2 treatments against one another. Here we can see that number B is slightly more effective than treatment A, and whenever we go back to baseline, that would be C, we see the previous pattern that was established during baseline. Right? So those are our 3 major design categories, and oftentimes in clinical research, we are then presented with the task how to interpret these data and how to make sense of it. And that is the big task of data analysis. And data analysis in single case experiments can take 2 different forms. We can visually inspect the data, and we would be looking for phenomena such as changes in level of the data, changes in trend, which I will explain to you in a little bit. And tomorrow we will dive deeply into what statistics are available. If visual analysis is not leading us very far, what can we do to kind of examine the data and find out if there is a difference or not? And there's a variety of parametric as well as non-parametric approaches to help with such a statistical analysis. So today we want to tackle this visual analysis, and visual analysis is the most common and most established form of data analysis in single case experimental designs. The approach is so established because the experimenter is online with the data as it is collected. Visual analysis has a long tradition. You are collecting data, graphing it, and visually inspecting that data as you do intervention, as you proceed with your entire experimental approach. Decisions whether you continue or you change or you end a particular set of procedures, that can be made on the spot. You can decide pretty much right away because you follow your data as you are collecting it. Visual analysis, however, is about eyeballing. You're looking at the data patterns with your own eyes, and because human beings are not always perfect, visual analysis itself may not always be perfect. That is, two professionals can look at the same data, but they still may not agree with what they see. Visual analysis is a very established, time-tested method. It's very widespread. It is often the basis of data analysis in single case approaches. You start with visual analysis, and then you can supplement it with statistical analysis on top of it. You are looking at the raw data, and these raw data, they are untouched. They have not been processed statistically. That gives it a very original, a very authentic flavor. You are presenting the results as they truly are. This is known as a very conservative way of making judgments. Statistics only tell you if something is statistically significant. Even a tiny change can show up statistically significant depending on how you deal with the statistics. But in practice, this tiny difference may not have a lot of what we call clinical significance. For the participant, him or herself, it may not make a huge difference. That's why there is a lot of discussion going on. How far should statistics go? Do we need statistics at all in single case experimental designs? Because what we typically try to accomplish is showing that things are clinically significant, that the intervention effect is not just there on paper or on the graph, it also makes a real world difference for our participants, and that is called clinical significance. When you visually analyze the data, two decisions essentially have to be made. Is there really a cause and effect relationship? Do we have experimental control between our treatment and the measured outcome? And if there is a treatment effect, what's its size? Is it sufficiently large enough that we would buy into this, that we would say this is actually beneficial and we are interested in it? There are two major difficulties when looking at single case experimental data. Often the amount of variability in the data. The data can jump up and down, can be all over the place, and there can be different forms of trend. The data can show different patterns, and we may not know right away how to interpret those patterns. Right. So the major requirement to do visual analysis is that you have a well-constructed graph. And when we review manuscripts for publication, for example, in the AAC journal or in other peer-reviewed outlets, we're looking for, is the data graphed correctly? And what do I mean by that? First of all, the data points need to be distinguishable. You as the reader can easily discriminate data points and data pairs. You should clearly separate experimental conditions. If I want to eyeball the data, if I read a manuscript or an article and I want to eyeball the data, I need to be able to tell what are the experimental conditions. Which one was baseline, which one was intervention, are there any subsequent follow-up phases, maintenance, generalization, and so forth, and have the authors clearly labeled those. The size and the relationship of the x versus the y-axis is very important in single case design graphs, because you don't want to clutter too many data points in a very narrow space. So the clutter should be avoided, and there should be enough space so that the data is not too cramped. And the legend, okay, I was off for a second. I think we are being reconnected. All right, let me briefly know if you can still. We lost you at the point 4. Okay, I will repeat from point 4. All right. In a single case graph, when the data are being graphed, there should be labels and legends for all the different conditions. And then, as I explained before, the entire graph should have very good proportions. You do not want to deceive the reader. The field that is available, the space that is available for the data points should be appropriate. If you clutter too much data on a very narrow space, you could easily confuse the reader, or you could give the wrong impression of a data path or a data pattern. Okay, here's a very good example for a perfectly well-constructed graph. We can see that the axes are very correctly labeled. We have on the y-axis, we have the dependent measure, the percentage correct of a certain task, and it's expressed in percentages. On the x-axis, we have the units of time expressed as sessions. And then the first data point, the second, third, fourth data point, they're all connected. Within a phase, it is mandatory to connect the data points with a line. Then you have a condition change line to tell the reader where does the new phase start. And then we have both phases, baseline and intervention, correctly labeled, baseline and reading instruction. And we have the data points in intervention being graphed very nicely, and they are also connected. So we can see a real data pairs, and we can compare baseline versus intervention easily by eyeballing the data. There should be a figure caption. What is this graph about? And in our example here, it's the percentage of questions answered correctly across baseline and reading instruction conditions. So this is the type of graph you would want to see in a manuscript, and that you as an author, you would want to produce to help your readers understand what happened and what the data are going to say. Right? Sometimes it's the challenge. You may be in the situation that you have an alternating treatment design, and the different data pairs are very close to one another, or sometimes they do overlap. Then it is recommended that you use different colors or you use different shapes to indicate which data pairs belongs to a certain treatment, and then other data pairs belongs to another treatment. Here we have a beta program and an alpha program, and there's white circles versus black circles, full circles, so you can contrast the two different data pairs. So that is the basic requirement. This is the basis. You have to have a very well constructed graph, and then you can proceed with visual analysis. You gather numerical data, and this is being graphed, depicted on the graph. And then you can use visual analysis to talk about how much of an intervention effect was there, and how did it occur? What happened during individual sessions. We would call that making formative as well as summative analysis of study outcomes. Right. So before you start visual analysis, ask yourself if this is your own data, or if you are reviewing someone else's work, ask yourself, are the legend, axes, and phases labeled clearly? Is the scaling of the appropriate? Like I said, you don't want to be in the situation where there is too much clutter and the data is not clear. Do the data depict the performance of an individual or the performance of a group being treated as a single subject? You need to know that up front, because if it's a group, a little bit of a change may be quite natural, whereas for an individual, a little change in a data pattern could already be a very significant step forward or step in a certain direction. Then you want to look at the range or variability of the individual performance. Is that also graphed in the group? Most of the time you will just see one person per data pass, but it is not uncommon these days that also the performance of a group is being graphed, and then you would want to know within the group what was the variability or the individual performance. So when we use visual analysis, we are interested in two specific types of patterns in the data. First, we're going to start to inspect changes within each phase or condition. And then in the second step, we're going to use visual analysis to inspect changes across phases and across conditions. We're starting small with just looking at what happened in an individual single phase, and then we're going to the larger picture, what happened across all the phases of the study. So I'll walk you through the within phase patterns, and there are 3 dimensions to inspect. We're going to be looking at the level of the data, then at the trend of the data, and then looking at any variability within the data. Right. The first dimension to consider is the so-called level of the data. By level, we typically mean the average of the data within a condition, and that is typically calculated as the mean or median, the mean value where you see the spread around when you graph the data. In other words, you could say it's the estimation of the central tendency of the data during a particular part of an experiment. You have conducted the baseline phase, and now the data are falling around a common mean. It is most important to look at the last few data points. They typically contain most essential information regarding level of behavior before there's a phase change. As an experimenter, you can expect that the behavior is most stable during those last data points, because over time, the participant will be less agitated, will have gotten used to the experimental situation, and the research subject will show the more stable performance during later sessions. So, in other words, level of behavior, again, we're looking at performance of the target behavior and possible changes that we can see going up and down vertically. Tony and Gerst suggested that if at least 80% of data points are around the 50% value range of the mean level line, then we would call the data stable, and we would call the mean level line acceptable. So I'll give you a few examples. Here we have such a stable baseline. So if we were to draw the mean line, it would probably be somewhere around here. And in the future, we would expect, if we were to continue this data collection, we would expect that this data collection goes along this mean line. That is essentially what this is telling us. And here the data points are very stable because they are within this 15% value range. There is not an outlier. We do not see data going very up or data going extremely down, right? The data are nicely spread along this mean line. So that is what you are shooting for as an experimenter. You are demonstrating a stable baseline. This is always the ideal situation. In practice, this is not what happens all the time. In practice, you may have lots of variability, lots of up and downs in the data. You can see different types of, we would call, I'll talk about this in a little bit, different types of trend. Here we have a somewhat stable baseline, but with a slight trend, but we can still kind of draw in that mean level line. And then we can compare this level to the level in an adjacent phase. And here there is much more trend because we are in intervention. We do expect the participant to improve. And we have another mean line that is our new level. And later on, when we're talking about comparing performance across phases, we are comparing this mean level line against this mean level line. That is this comparison. This visual comparison is the comparison by level, the jump from one level to another. That's what this part of the analysis means. Comparing the level identifying the level of the data and then telling that the level is at such a range or is at such a level, and then it jumps up. The performance goes from this low level to another much higher level. That's how you would explain it then in the manuscript. So in addition to level, you can have phenomena where the data are slightly increasing or decreasing, or there is a very steep slope. They go up very quickly or they go down very quickly. And these phenomena are called trend. We're talking about trend in the data. And there's two distinct elements within trend: slope and magnitude. Slope means, is it going up or is it going down? We're talking about a positive upward slope if the data are continuously increasing, and we're talking about a downward or negative slope if there is a constant continuous incline. The data are decreasing step by step, right? Then the size or extent of the slope can vary, and that is called magnitude. And you can qualitatively describe that magnitude as high, medium, or low. You should use this type of terminology in your manuscript, and you should say visual analysis of the data revealed a rapid increase, a high magnitude slope during this phase and that phase, or so forth, right? And I'll give you an example tomorrow how to write this up actually. So anyway, back to the topic. The magnitude can be expressed as high, medium, or low, and a high magnitude slope, you can also say there's rapid increase, rapid decrease in performance, and for a low magnitude slope, you can also describe this as there's a gradual increase or a gradual decrease in the data. So this one here would be a high magnitude, high increase in the data, and here we have a low magnitude slope, a very gradual slight increase, right? Okay, I think I jumped about this. This is the same example here. You can also visually display the trend by constructing a so-called trend line. This is not mandatory in manuscripts. As a matter of fact, many journals don't even want that. But if you feel like you need to guide your reader or you need that guidance for yourself, you could, and I'll show you how this is being done later on, you could draw in the so-called trend line. Then this is clear that there's a change in slope, there's a change in level here, and in addition, there's a change in slope going from a low magnitude to a high magnitude slope. Right? This is an example for what we call increasing trend. If we were to continue this into the future, if data collection were to go on, we would expect that this trend goes goes on, continues along this slope. That's what increasing trend means. Decreasing trend is the same phenomena, but in the opposite direction. We are starting out with a high target behavior, and this is being decreased over time. It gets less and less and less, and then baseline is becoming less and less here, and projected performance into the future would be, we would be assuming that this trend further decreases and goes down to 0 baseline levels. So the greater the slope, the less meaningful level is as a general estimate of the data pattern. What this means is if you have highly increasing or highly decreasing data, things are going to change pretty fast. And then indicating the mean level of performance is no longer that valuable information because the participant is moving away from that mean very quickly. That's why it is important to talk about the slope in addition to the level. And like I said before, you should be judging the trend. Simultaneously, you estimate the slope and magnitude of the data. For example, you could write data has a strong positive trend or it has a strong negative trend if it decreases. Later on, tomorrow I will talk to you about linear regression. That is a statistical approach, how you can actually express the magnitude of that slope, but you could also draw in the middle line, the trend line, and that can be done relatively easily by using a procedure that is known as the split middle technique. We will later on, we will see how that works. Okay, so now we need to talk about the third phenomenon that we are examining during visual analysis within a phase, and that is the variability of the data. By variability, we mean the degree to which individual data points deviate from the overall trend. The data points are sort of scattered in a phase. And if there's a lot of scatter, then we would talk about a lot of variability in the data. If the data are falling nicely along the same path, then we have very low variability. And that is actually the more desirable aspect, that there is very little variability. So there is a question. So can you put the question in the chat, please? And I'll see if I can answer it. Please, can you explain how you get the trend line on slide 29? Yes, that is the blue line. Yes, it could be done with the blue line, or it can be done with the green line. This is done by using the so-called split middle technique. And later on in the slides, I will show you, it's on your handout, and I will show you how this is being done. All right, just hang in there. We're getting to this. We're getting to this at the end of the session. Then I'll show you how this is being derived. All right. Good. Let me continue talking about the variability. So this is how the data are being dispersed. And you can talk about variability as high, medium, or low. And like I said, the greater the variability in the data, the more data points are required to document a consistent pattern. If everything is very clear, and if if the data are not scattered so much, you need fewer data points to make your case that there's a stable performance, that there's a stable baseline, or there is enough data points to show an intervention effect. However, if the variability is very huge and the data are scattered all over, then you need to continue with data collection so that you have a clear path and that you can see a clear trend. All right. So here we have a few examples for variability. In this baseline, for example, the data are all over the place. They're almost reaching the ceiling. And then it's very difficult to establish an intervention effect because in the intervention phase as well, there's also lots of variability. We are starting very low and then the performance goes up also to the same data point up here. We could also say there's lots of overlap between these two phases. And because of this amount of variability in both phases, it is difficult to make the case for an intervention effect. Essentially, the data pattern did not change a whole lot. The data is scattered all over the place in baseline, and the data is scattered all over the place in intervention. We don't necessarily have a good argument to call this an intervention effect. An example for a variable baseline, the data are jumping somewhat up and down. What researchers should do in this scenario is to continue for a few more measurement occasions, add on a few more sessions, till eventually the baseline is going to get stable. Now, you might never get to this point with a participant whose behavior is very erratic and it cannot get under control. Then two different options. You can stop it at some point. You should actually stop it at some point for ethical reasons, and then hope for that during intervention you will be getting a jump in level and much different data that is at a higher level and clearly going in a certain direction that you could aim for. Or if the participant is completely erratic, then essentially he may not be a good research subject. It means you have no ways of getting his behavior under control. I'll show you such examples in a little bit as well. And then clinically you should still work with them, but for the purposes of showing a treatment effect, the scenario may not be what is working for them. They may not be a good candidate for an experiment in this type of sense. Right. There can be phenomena such as an increasing, decreasing baseline, where initially there's a little bit of an incline, and then after so and so many sessions, there's a decline in the data. This typically means something is going on during the middle, where the participant experiences, we call it a covariate, something else that has nothing to do with our treatment, our data collection, something else influences the participant. It could also relate to this phenomenon the other way around, a decreasing, increasing baseline, initially going down, then going up. And the reasons for this can be manifold. There could be that on certain days, a person is being present who is not perceived as being nice. The participant cannot stand that individual, or there are other days of the week where something funny happens. There's a birthday celebration or something, and the participant is in a better mood and is more willing to respond. Typically, it's due to some external circumstance. It could be also something such as medications being given on a certain day, or being on and off, some additional treatment that interferes. You have to be very careful. If you can find out what that covariate is, it is best if you can eliminate it, if you do not have that disturbing influence on your data collection. If you cannot eliminate it, there are still ways of demonstrating an intervention effect if you have such a pattern, curved linear pattern in your data collection. Again, an example for a very unstable baseline. And what you should be doing here is either you continue it till it gets stable, or you can implement treatment and hope that treatment is going in a going very quickly in another direction that clearly is different from this baseline. Right. So to sum this up, we are looking at three different things: level, trend, variability, and we are describing these three phenomena within each phase of the study. And you want to qualitatively express in the manuscript how do these dimensions change across phases. We've talked about different patterns that might also occur: a curved linear, a U pattern, an inverse curved linear data pattern, inverted U pattern, or a cyclical data pattern. And these are typically indicators that on some measurement occasions there is an external influence, a covariate that we haven't planned for, that is influencing how the participant behaves. And that, if you can find it out and you can get it under control, that would be the ideal situation. If you cannot get this under control, then you continue data collection till it is somewhat stable, and hopefully you can show that the intervention effect is going in a different direction, or is going in a certain direction very quickly, so you have a different pattern than what you've been seeing here in those phenomena. All right. All right, so now I talked about describing the data patterns within a phase. Now we need to talk about describing data patterns across phases, and we would call that between phase or conditions patterns. Here we have a few more criteria to consider: the number of data points within a phase, the variability in performance across those phases. Are there changes in the level of behavior? Are there changes in the trend? How do those phases overlap with one another? I've lost the slides. Can someone put the slides back on? All right, perfect. Here we go again. So I finished here. We need to look at overlap in data sets from one phase to another. We need to make judgments about how quickly or immediately did we see a change from one phase to another, and can we identify the same patterns across phases or different patterns across different phases of the study. All right, so let me start with the number of data points. There should always be enough data points within each phase so that you as a reader, or that the audience, when they are looking at your manuscript, that the audience can clearly determine what is going on. The audience needs to be able to tell whether the data pairs accurately represented performance on the dependent variable. Right? So here we have only 3 data points in baseline, and that is the minimum number of required data points. If you have less than 3 data points in a phase, this is not believable. We would not have certainty. We would not call this valid data collection. You need at least 3, because that is the minimum that you need to see some type of trend. You cannot establish a stable pattern if you have less than 3 data points, right? Most manuscripts, most journals nowadays, they will tell you if you can collect at least 5. 5 is better than 3, right? You have more opportunities to show what the data pattern is and what direction the data is going. So here we have 3 data points with some variability in there, and then we have more data points with lots of variability in that second phase from baseline to intervention. All right. So the same data, but now imagine we have continued, we have collected more than 3, and then during the last 3 we can see a very increasing trend which we haven't seen before, and now our interpretation changes completely. In the previous pattern we would have said, yeah, okay, there is some change in the level. This is the mean level here, and the mean level would be about here, so there is some jumping up here from level in baseline to the level in intervention. We would see that, interpret this as an intervention effect. But once we collect more points during baseline and we can see this increasing trend now the intervention effect is no longer so believable. We wouldn't say with certainty that this is truly an intervention effect because we have lots of overlap. The participant is already moving in the direction of treatment. So maybe it didn't really make a difference whether we had put on treatment or not. The participant would have been going in this direction anyway. Right? So that is why as more data points there are, as better judgments we can make, as more certainty we have that the participant is leaning in one direction or another. Okay. Many data points collected here during baseline. The baseline is not stable at all, but like I said, if you can show that in intervention there's a completely different pattern, then this still makes for a believable intervention effect. Relatively stable over time, yeah, and then as soon as intervention comes on, we are seeing this very steep incline, and that helps us to make the case for an intervention effect. But we would not have been able to do that if we only had like 3 data points or even less than that. So number of data points, very important. We've already seen in these previous examples how important it is to look at variability in performance. If an individual exhibits little variability in performance or a steady data path with a clear trend, then the researcher may rely on fewer data points. However, if you have a lot of variability and you need to continue, when the performance fluctuates, then a greater number of data points is needed. The key point is you need to collect as many data points as possible to see a clear direction, to see a clear difference in trend, and to see a clear difference in level. Right? So this is not very ideal. The participant in his or her performance is all over the place. Sometimes he is reacting strongly, other times he is not responding at all or responding very lowly, at very low levels. That is not really clear where the participant is, in what direction he is going, what is he leaning to, right? This is a much better preferred way. But you cannot force your participant to behave, of course. But this is what you would be looking for as a single case experimenter, that the data patterns are very stable, are somewhat clear cut. It is obvious from this example, from this stable performance, at what level the participant is currently at. Good. Then the same phenomena are being talked about, level and trend. Level refers to the performance of the target behavior and possible changes that would be viewed vertically. I've already mentioned that. So we can use a different scenario here. a high frequency behavior, number of errors to start out with. Student makes a lot of errors as before we are starting treatment, and then we're having two different intervention options here, intervention option A versus B, and B is superior to A because we see that the number of errors is being reduced very quickly if B comes on, and if A comes on, the reduction is not as. And we can tell that by looking at the level, the lines here, the level lines. We have the mean level line for baseline, and we can compare that to treatment A, and we can compare it to treatment B. And clearly, this is a larger jump. We are seeing more of a difference when this version of the treatment intervention comes on, and we are seeing very less of a change in level when the A version comes on. All right. And then again, also we have to talk about trend across phases, and this is done by examining the direction of the data pairs. Okay. Again, we can draw in the trend line, and I'll show you how this is being done. Here the trend is stronger. It reduces the target behavior much faster, much quicker than this one reduces the target behavior. So you would use that type of analysis to make your point again that this one, version B, is superior to version A. Right? You could also draw in the trend line in here and then see that there's no trend or just a very slight trend. And here you have a medium trend or a highly decreasing trend in version B. So you're making those statements to compare the two different phases and make your case for an intervention effect. Or in this case scenario, which one is superior. So then the next criterion, we, if possible, in an ideal scenario, we do not want to see a lot of overlap in the data between different phases. If you go from baseline to treatment, the overlap between that data should be minimal. And you can express that as a percentage or a degree to which data in adjacent phases share similar qualitative values. You have to be very careful with this type of analysis because you could be in a scenario where there is no overlap but a lot of trend, and that is still problematic. In such scenario, the trend criterion overrides the importance of overlap in evaluating the functional relationship. I'll show you an illustration what is meant by that. Let's go back to our initial scenario first. So here between the pink data points and the dark blue data points, we can see lots of overlap. Again, this points us towards saying this treatment, this version of the intervention treatment, this is not so effective. And this one here has very little overlap. This is the only data point that overlaps with baseline. So this is much more effective because of not having that overlap with that phase, right? But here's the scenario where you really have to be careful. You have very little overlap, only this data point overlaps. So from the overlap criterion, this would be a very effective treatment. But if you're looking at it from the perspective of the trend criterion, the trend is already going in this direction. You see a highly increasing trend here during baseline, and this continues into treatment. And that is not a good thing, right? This is not what we would like to see. We no longer have evidence for a functional relationship. The participant is going in that upwards direction anyway, no matter if I'm putting on treatment. And the demonstration of an experimental effect is now being ruined. This is not a good baseline. If your objective is to increase behavior during treatment, but the baseline is already going in this direction, then this means the participant would have improved either way, no matter if there is treatment or not. So it's difficult to say there's an intervention effect, right? All right, not a good baseline, not a demonstration of an intervention effect here. Okay, so the last couple criteria, they are about latency or immediacy, and then later on about consistency of data patterns. Latency or immediacy, what does that mean? This criterion is about when does the change occur. In a very potent, in a very powerful treatment, you would want to see a change in the data pattern relatively quickly. As soon as you're putting the treatment on, you would want to see a behavior modification. But sometimes it can take a very long time before the participant reacts to the treatment, and this is called latency. And as longer this latency is, as longer we have to wait before the participant reacts towards the treatment or intervention, as less convinced we are that the treatment was responsible for the change in behavior. So this is the official definition. And this is known as an immediacy of effect or rapidity of change. In other words, how quickly a change in the data pattern is produced once you put treatment on and once the phase changes. The greater the immediacy effect, the briefer a phase can be, and the more convincing is the functional relation. If the change occurs relatively rapidly and you see an immediate uptake in behavior or immediate decrease in behavior, if that is your objective, it's more convincing. And then you don't have to demonstrate it so often. You can stop data collection a little bit sooner. So here's a little bit of an extreme example for lots of latency. We're starting with a high target behavior, here the baseline, and then at a certain point, treatment comes on, but you see lots of overlap for many sessions, and then through the middle of the treatment phase, this is when things are going to change. They're going back to baseline levels, the performance going back here, and then it goes back down at the very end. So the treatment effect is almost not present. There's very little change that the treatment is causing for the participant, and we're calling that latency. This is not a convincing demonstration anymore of an intervention effect. It could be that the changes that we're seeing here, that they are due to developmental effects. The participant is growing into this direction anyway by maturation simply. It could be something else happened over the history, over the course of the experiment that causes the changes seen here at the very end. The latency is a problem in this type of scenario. Good. This is the better scenario. The opposite to latency is immediacy. As soon as you're putting treatment on, intervention comes on, you're seeing a very rapid change from high baseline to lower levels here during intervention. It goes down relatively quickly, and it stays there. Then you're comparing this to here. You're putting baseline back on. The treatment is withdrawn, as I explained in the very beginning, and you're seeing the same pattern very rapidly. So there's a lot of immediacy. Same here. Immediate once you put intervention back on, immediately the data pattern goes down. You're seeing the same phenomena in this phase than you saw over here, right? That is an immediacy example. So we want to apply these types of criteria across the different phases. Immediate change is always good to see. Then it's very clean cut. Overall level should be, you want to compare that for each phase, and then how does it compare with other phases? The changes in trend should be compared from one phase to the subsequent phase. So this is what this graphic is supposed to tell us. The circles is what you're comparing to. You want to see this immediacy effect, and the boxes, and here the triangles. You're comparing always this against this, this against this, this against this. You want to see differences in level and trend, and differences here in how immediately, how quickly this is going up or down, right? These are the consistency patterns. Essentially, this is now becoming a matter of consistency. Consistency of data patterns across familiar phases. That's what this graphic was showing. In intervention, we're having consistent data patterns, and in baseline, we're having also consistent data patterns. Yep. So another illustration, you're comparing baseline 1 to baseline 2, or intervention 1 to intervention 2. And if you see the same type of data patterns, you have a more convincing case that there is a treatment effect. Basically, here is a replication of what you've been seeing here, and this is the second replication of this intervention effect. You're looking for these consistencies. Now, this is being demonstrated with an AB design, but in a multiple baseline design, you would just look vertically. You would compare the first AB phase to the second and the third AB phase. So it doesn't matter how those AB phases are being displayed or how they are being aligned. Good. I talked about trend a lot. Remember, trend gives you an indicator in what direction the desired effect is going or is not going. And we can get a better handle on trend if we are putting the trend line into our data. And this is known as computing the lines of progress, or as the so-called split middle technique. The trend line provides an indication of the direction of behavior change in the past. And also it tells us if we were to go on with that phase, what would happen in the future with the participant if this were to continue, so to say. And you've asked me before, how do we actually compute, how do we construct this trend line? And we're using a technique for this that is known as the split middle technique. This technique reveals the nature of the trend in the data and can be used to make and test predictions about changes in performance over time. So we can break this down in different steps. Your first step, when you have the graphed data for a phase in front of you, is you divide the number of data points in half by drawing a vertical line down the graph. So imagine this would be one phase. One phase could be treatment, could be baseline, whatever, right? So then you're taking this one phase and you're dividing it up in the middle, so that 50% of the data are on the left-hand side and another 50% of the data are on the right-hand side. Then your next step is, on the left and right halves of the graph, find the mid-session and draw a vertical line. So you're doing the same step one more time. In each phase, find the middle point and draw another vertical line, split up each subphase in another half. Okay. So now you're going to be looking at the y-axis and you want to find the mid-performance point, and you're going to draw a horizontal line. So within this half, where's the mean performance? It's somewhere here between 10 and 15. And I'm drawing another middle line there. And then in this half, where is the mean level of performance? And it's somewhere here between 20 and 25. I'm drawing another mean line over there, and I'm looking at these intersections. Where do these two lines, the vertical and the horizontal line, where do they intersect? Those points are now being connected. Draw a line connecting the intersections of both halves of the graph. This is the trend line for the data. So you're taking this point and taking this point, and you're drawing a straight line through those 2 points, and that is that trend line that you have seen on those previous examples. If you do not want to do this by hand, there are a certain graphic programs these days. One is called Prisma. There's another one that I'm blocking on that will actually do this for you if you don't want to do it by hand. But most researchers these days, they are actually still, if they're doing it, they're identifying those points and drawing it in just manually. It's probably the easiest. So advantages, to sum this up, advantages of visual analysis. There is a certain social significance. It's a very conservative method of looking at the raw data and actually saying whether or not it was really clinically and socially significant. You're more likely to identify independent variables that produce strong or socially significant results through this very conservative method. It encourages the reader and the researcher to carefully examine every aspect of the data. You've seen how many different criteria there are, from the level, trend, variability, over to consistency, immediacy, and so forth. You're really examining every aspect of the data very closely, looking for overall sources of variability rather than just overall effects. So you're dissecting the data very carefully, and you're interpreting it in multiple directions. This is different from just running a statistical test that tells you, is there a significant difference, yes or no? So, but you don't get more out of the stats test. Visual analysis allows you to paint a very fine-grained and detailed picture of what you can see on the data, with the data. Statistical analyses oftentimes require certain assumptions. How is the data distributed? How is are the data points related with one another, yes or no? And then sometimes we can't apply statistics because we don't meet those assumptions. We do not have enough data points and so forth. And then visual analysis is much more flexible. The requirements are not as big. You need to have a minimum amount of the data. We've talked about this, at least 3 data points in the phase, but then already you can start applying visual analysis. The data should be graphed nicely and properly. That is a basic requirement. But other than that, visual analysis has no prerequisites, so to say. The limitations, the downside to visual analysis are that it might not be as reliable as statistical analysis because it relies on the human's capability to eyeball the data, and different people have different skills. One person can be an expert at visual analysis, another person may not be trained as well in this method and can derive erroneous statements. There has actually been some research into how reliable is visual analysis, and there is a certain likelihood that different observers would make false statements. We are calling this a type 1 error. They are concluding that there is an effect when in fact there is not an effect. And these type 1 error rates, they can range from 16 to 84%. Makes sense. Some people are very trained, they are very accurate, they can apply these criteria very precisely and consistently. They have low error rates. And then some folks who are new to this and do not know how to do this, have never heard about trend level and so forth, they make lots of errors, and they may arrive at the wrong conclusions and then the error rates can be as high as 84%. Right? All right, so let's finish off the day with some examples and some exercises. I still cannot hear you, but I'll give you a few minutes of reflection. In this first exercise, I want you to look at this graph. It's a multiple baseline design. We have 3 different baselines, and then an intervention is being on. Social type of intervention story is supposed to increase the intervals with on-task behavior. The social story tells the students how to properly engage in task completion, and this on-task behavior is supposed to increase during intervention. And this is from a real manuscript. This was submitted for publication, but it was rejected. And I have obtained permission to discuss this in class. And my question to you is, what went wrong? Why did the editors reject this type of manuscript? So why don't you speak with your neighbor for maybe 2-3 minutes, and then give me a little bit of a heads up when you're done, and then I can present you with the solution. Yeah, all right. I'm seeing a lot of good and correct comments there on the chat. Many of you have said the baseline is unstable, and that is essentially true for all three baselines. They are all unstable. The first baseline, the first contrast, A versus B here, is somewhat believable because we are seeing a big change in level. If we are putting in the level, mean level here, it would be somewhere around here. If the mean level for the intervention here would be somewhere up here, that I can believe. This is still acceptable as a demonstration of an intervention effect going from A to B in here. The second and the third, however, are very problematic for various reasons. The biggest mistake being made here for number 2, for Jack, is that the baseline doesn't start with all the other baselines. That should, all right, you guys need a minute because the connection needs to be reestablished. All right, so you got my first point. This is believable because there is a change in level from a mean level here to a higher level up here. Number 2 and number 3, Jack and Nolan, are not a good demonstration or not a believable demonstration of an intervention effect. First of all, this empty space here is incorrect. The baseline should have started with all of the other baselines. Essentially, we don't know what's going on in here. There could also be data that is falling around the higher levels of performance, and that would create overlap like in this scenario. So this is inappropriate. And then we've talked a lot about trend. And if we were to put in the trend line for this second baseline, the trend line would fall around this pairs. And if the baseline is already moving in the direction of treatment, then the treatment phase is not so believable. And this is the scenario that we have here. The last 3 data points are increasing, and these data points here in the middle too are increasing. There is already a jump. Regardless of treatment, there is already a very increasing data pattern. We would actually call that a high magnitude slope, and this continues into treatment. So in other words, the functional relation experimental control is compromised. We have reason to believe that the participant would have made that change either way, no matter if treatment was on or off. And then you've correctly talked about overlap for number 3. If we are looking in the dispersion of the data points, in baseline for number 3, there's a 5% up to 90 or 95%. So almost the entire scale is covered during baseline. What that means is there's so much variability that it is almost impossible to show an intervention effect. There's complete overlap with the data in intervention, and again, we would not believe. It's just not, there's no point in saying treatment made a difference because there's no change from here to here, right? So this is why this manuscript was rejected. You covered it very well. Thank you for your answers. And now you can just type in the chat. I'll show you a few example graphs, and you're telling me, is there an effect or no effect? And again, we want to compare phases across the entire experiment. We want to do between phase comparisons. So we're looking at baseline here, treatment, then reversal, and then treatment. Do we believe there is an intervention effect? Yes or no? There's no effect here because we have these decreasing trend lines going all the way through, right? We would want, as when reversal comes in, that this goes up to baseline levels and then down again, but this is not the case. And throughout all these phases, we can observe the same decreasing trend. So no effect. Okay, next one. Do you think this is an effect or no effect? Yes, correct. You would say that this is an effect, and you're right. You have a slightly increasing baseline, treatment comes on, and you can see a strong effect through a high magnitude slope, and then the exact same thing happens. The reversal effect is being shown when we are withdrawing the treatment. These patterns, we can compare consistency. This one is consistent with this. And then when treatment comes back on, intervention effect is replicated. This one is consistent with this one. So good demonstration of an intervention effect. All right, let's look at this one. Effect or no effect? People are still thinking. No effect. No effect is the right answer because you have too much overlap between these baseline phases and the intervention phase. If intervention is supposed to decrease the behavior, these intervention phases should be much, much further down. They should be really showing a decreasing trend that reduces the high baseline behavior to nearly zero baseline levels, and that is not the case. We have too much overlap in all of the data strands. Okay, this is maybe a little bit trickier. Effect or no effect? Yeah, you folks are not sure, and this was a mean question from my end, because indeed visual analysis alone is probably not going to help us out here so far. This is now a good scenario where we might want to supplement visual analysis with statistical analysis to really see if there is a difference between the two treatments. It's that alternating treatment scenario, and we have one treatment that starts out looking superior, while the other treatment starts looking inferior, but then sort of it reverses. Number C starts becoming better while number B fades out, but at the end they are very close to one another. It could be that the statistical analysis will reveal there's no significant difference in between them. Then the conclusion might be it doesn't really matter what intervention or what treatment you provide. In either case, there is somewhat of an intervention effect. That could be the conclusion here, but we don't know for sure unless we do a statistical test. Right now, they seem to be producing around the same type of change for the participant. In such scenarios, it is also recommendable to really ask the participant if they had a preference for one version versus the other. We might, in the end, choose the one that is more socially valid, that was more socially appealing to the participant and is actually validated by the participant or by the stakeholders. Okay, so that was a little bit of a trap question from my end. And next one, similar scenario, but now different data pairs. Do you think this is an effect? Is one superior to the other, yes or no? C is better. That is the correct answer. Because of that stable upward trend, you have what is called a clear phase differentiation, or a clear differentiation between the different data pairs. And in an alternating treatment design, that is what you want to be looking for, that consistently one treatment produces better results than the other one, than the alternative option, and C is clearly superior in this direction. And so we would say, yes, there is an effect, and the effect is C over B. Okay, that was it from my end. We still have like about 10 minutes left for any questions. Yes, I use software to draw the graphs. I do most of the graphs in Excel. Like I said, there's another two software packages available. One has something in the name with Prisma graph, and there's a third one that I'm blocking on that you can also use to construct the graphs. I can have that information for you tomorrow in our second day session. Typically, Excel is sufficient. Most universities have Excel either way as part of the Microsoft software package. Do you have a reference for group data that used SSCD? I have to look this up. Those scenarios are relatively uncommon. One example I can give you is is traffic research. When people are being monitored, how they behave at intersections, how car drivers are reacting towards pedestrians, for example, when they cross intersections, or what happens at a very busy street. Then the group that arrives or behaves at a certain time interval, they can be graphed as one unit. And then over time, you can graph that traffic behavior, and you can graph that, you can do the same thing that you do with a single case experimental design, show the behavior of that group, the traffic participants, so to say, and then something is done, an intervention is done, the signs are being changed, the traffic lights are being changed, and that changes that behavior of that group, the traffic participants. And this, they are still, also there are different, there are several participants, they're always graphed as one group. That is a common usage of single case designs for a group scenario. In the behavioral sciences, I don't see it a lot. In our cases, in communication sciences and disorders or special education, I don't see it a lot that groups are graphed, are presented as single cases. All right. All right, thank you very much. I have appreciated it, and you have been participating very well. You did very well on the exercises. That was very nice. I look forward to seeing you. There's one last question. Yeah. How many data points does one typically need in an intervention phase to show an effect? So this is a very good question. There is not an easy answer to this. So at a minimum, at least 3 for the requirements of visual analysis from the perspective that we've taken today. So at least 3 to show that there is a change in level, a change in trend, that the data is going in a certain direction. However, it depends a lot on your clinical scenario and on the nature of your intervention, how many sessions you think should be done. And that is a question of setting a so-called mastery criterion or a so-called teaching criterion. So before you start your experiment, you want to think about the nature of your intervention. How likely is it that with this intervention, the participant reaches a certain degree of mastery? Is the reading instruction going to lead to mastery within 5 to 6 sessions? That would then dictate that you're saying, okay, there is a certain likelihood to reach those 5-6 sessions by in 5 or in to reach that mastery in those sessions. Then you're going to set this as a teaching criterion. You're going to say, I'm teaching exactly 5 or 6 sessions, and that's how much is typically needed to reach 100% mastery. If you can't tell that, then you would want to say, I'm aiming for mastery, and mastery is when 80% or 100% or 90% of the y-axis is being fulfilled. And I'm demonstrating this 2 times in a row, for example. So either you're setting a mastery criterion, how far on the y-axis do you want the performance to go, and the participant either reaches that mastery criterion, yes or no, or you are certain that in given amount of time, the participant will have reached the intended goal. Then you're setting this as the number of sessions. That is actually, from a clinical standpoint, this is the more legit way, the more meaningful way of deciding about the number of intervention data points. You should not do this just on a feeling out of your stomach or something like that. You should be justifying those intervention data points in a meaningful way. Okay. All right, those were all excellent questions. If there's not anything else, we can call it quits here. You're most welcome. I have enjoyed talking to you. I will see you again tomorrow at the same time, and we will go further into some of the statistics behind this. Thank you so much, and we will see you tomorrow. Bye for now.